Okay, so this video I'm going to talk about multiple regression. Probably do one of the same examples I did in class today, and just discuss a few other things. So multiple regression is, as it says right here, is an extension of simple linear regression. And your theoretical model will look something like this, where Bn is the nth coefficient. It's a number in front of whatever xn is. I have multiple x values. That's why it's multiple regression. And when I get much over 2 dimensions, I go to 3 dimensions, that would just be 2 x's. Beyond that, we can't really visualize it. So we're going to do some examples in Excel and StatCrunch and see where we go. So we talked about coefficient of determination, r squared, and it's a percent of the variation of y explained by the variation of x. And that, is telling us how good the model is at explaining how y is changing as x changes. Another measure is adjusted r squared. And I mentioned this one in class, but it has a little more added to it. It's also looking at the efficiency of the model. Now you can pause it and read this if you want. I'm just going to scroll down to this right here. And here I have some data points that look fairly linear, and you notice I have a 5th degree model fitted to it. And you can also notice that the coefficients on the x5 and the x4 are very small. If I look at the models I chose, line, quad, cubic, quartic, quintic, and the r squared keeps going up in value. So as I add extra terms to the model, this would be like y equals x squared plus an x, y equals x cubed plus an x squared plus an x. You get the idea. The r squared keeps going up. That's going to happen for any model. If I just keep adding in regressors, if I keep adding in x values, my r squared is always going to increase. But if I look at adjusted r squared, it's taking into consideration the efficiency of the model. These two variables really aren't contributing much. You can even make maybe an argument that x cubed is not contributing much. So when I look at a line, that adjusted is 0.995, 2, and quadratic, it actually went down. So going from a line to a quadratic, I'm very close, but my adjusted r squared is going down. And that's telling me I don't probably really need the x squared. Well, if I add an x cubed to it, well, it went down some more. If I add a 4th degree, 5th degree term, it just keeps going down because I'm adding in variables, trying to explain stuff that's not mattering. So I did not do this example. It's a standard one that I've done in the past. We have calories, protein, fat, carbs. We're going to make a prediction for calories, so this would be my y, for protein, fat, and carbs. I could call this x1, x2, x3, or x sub p, x sub f, x sub c. Or you could use the words. It doesn't matter. So however I do it in Excel or StatCrunch, this is what the output would look like. In this example, this is an Excel output. And there's my r squared. Here's my adjusted r squared. And when I see a drop like that, I know that some of these variables aren't that important. 0.77 is not, in my opinion, super great, but is not bad. Coefficients, these are the coefficients for my model. And why don't you maybe pause this, take a look at it, and bounce back. I'll bounce back myself. My equation would look like this, and technically it's y hat is equal to these coefficients times the variables. And if I scroll up very slowly, here you have the equation, here you have the coefficients, and you'll have to do this on the final from an Excel plot or output. Match up the coefficients with the actual variables. That's your equation. That's your model. If I give you some values, carbs equal 12, fat equals 5, protein equals 6, I would plug those into my equation and get a predicted value. So a combination of 12 grams of carbs, 5 grams of fat, and 6 grams of protein would return 172 calories approximately. But again, adjusted r squared is 0.77. Not a great model. Okay, with that aside, you have to be able to do global tests and individual parameter tests. So a global test, as I stated earlier, is H0 comparing all the betas except the intercept all equal to 0, and HA is at least one beta is not 0. Failing to reject is saying that all my betas may as well be 0. If I scroll back up to my model, that's saying that I may as well just get rid of these numbers and throw zeros in there. And if I do that, I'll just get the intercept. So that's telling me my model is not adequate. Adequate is kind of a misnomer. Excuse me. It just says, is it somewhat useful? It's not saying it's a great model. Is it somewhat useful? Well, for our process, I would have H naught B sub C equals B sub F equals B sub P, carbs, fat, protein, all equal to 0. HA at least one beta is not 0. If I scroll back up, significance F is always going to tell you the p-value for the global test. And that's very small. That's like a 0.17%. So I'm definitely going to reject the null. And when I reject this null right there, that's telling me at least one beta is not equal to 0. So at least one of these coefficients is needed. That tells me the variable is needed. So it's adequate. The next step we have to do is actually going through and testing each individual beta. So bring this down. I have 3 different x's, so I'm going to have 3 different hypothesis tests. Beta sub P, beta sub F, beta sub C, carbs, fat, protein equals 0 against not equal to 0. When I reject in this case, I'm saying that beta P is not 0, therefore the protein is needed. So scrolling back up. For carbs, my p-value is 0.59%. For fat, my p-value is like 2.1%. And for protein, it's around 88%. That's high. So I scroll back down, put in my p-values. P-value for protein is 0.88, so fail to reject. That's telling me that I probably don't need to use the protein data in this model. I could do just as well without it. Beta sub F for fat, p-value is around 2%, so that's rejecting. That's implying that the variable, the x for fat, or the variable for fat is needed. I'd also reject for beta C, so the carbs are needed. And one thing I want to mention is the smaller the p-value, the more important it is to the model. So this is telling me carbs is way more important than protein. Fat's a little bit more important than protein, but carbs is the main one telling you the prediction for calories. So if I wanted to, I could go back and refit the model and not include protein and get a whole new equation. And then I wouldn't have to actually go through the rest of these procedures because we've already shown that the model's good. I would probably ask you to on a project. Here's one, and I believe we did this one in class, another set of data. And I'm just going through on this handout how I did it in StatCrunch. I have a different video on that. I just want to get to the output. So the output from StatCrunch, I'm not going to argue, is better. I just want you to be able to deal with the Excel one. It spits out the model for you. It writes it all out. They're getting the coefficients from here, just like we did today, but it's written all out for you. It's giving you your R squared, your adjusted R squared. I'm seeing this is 0.99. When these are that close and that high, more than likely the variables are all needed, but not always. I think in this one a couple of them aren't. First thing I would do is the global test. So here, beta 3 equal beta 2 equal beta 1. Now, I'm doing this as 1, 2, and 3. You have to keep straight which one's what. And to be honest with you, when I wrote this out, I don't remember. I would guess this is 1, that's 2, and that's 3. That's typically what I do. I go from left to right. But I look at the p-value overall, 6%. 6 is less than 10. If I use that for an alpha, I fail or I reject. That means the model is adequate. I would continue with the process. Okay, so here I actually did the abbreviations, which is what you should always do. I have my 3 different variables I'm testing. I have the p-values written out. 0.03, so 3%, I would reject. That implies that mg is needed. 18%, that's pretty high. I'd fail to reject. 16%, that's pretty high. I'd fail to reject. So that gives me evidence that I don't really need either temperature or ratio. I could go back and refit the model, getting rid of these two, and just redoing it with MG and see how good the R squared is. It probably wouldn't change much. And you can see that the model is a pretty good one. Getting rid of a couple would make it a little bit more efficient. Okay, you will have to go through this process on the final, and you will be using an Excel output. You're not going to actually have to calculate it yourself. I'm just going to give you the output.